So in the last lecture, we had discussed about one of these very deep neural networks, and this was the GoogLeNet, or this was the first time that you saw that while counting over VGGNet, one of the major advantages which we got. So there were two important aspects in GoogLeNet which we had done. One was that this had different kinds of receptor field in terms of your inception models, where you could have 3x3 kernels, 5x5 kernels, and 7x7 kernels. So you were in essence what you were doing is you were going down over larger spatial spans, and also you had 1x1 kernels which were trying to do some sort of a combination across all the channels of one given pixel over there. Now what comes out over there was you were able to get down like different receptor fields, and then which goes on passing, and then eventually like there was this whole hierarchical combination along the depth over there. On top of it, next major thing was these auxiliary classification arms, which allowed you to actually do some sort of a gradient boosting or feedback extra amount of error onto it whenever there was a chance that the error keeps on going down, such that you can train it. Now the model which we had studied was the vanilla model, which was directly reported down on the GoogLeNet paper for the first time, but the one which we are going to use today is a bit different. So this is the model which we are going to use, and this is something which is based out of PyTorch. So you the link for this one is provided directly over there as well, and this is from the PyTorch documentation. Now the difference over here is that it does not have two auxiliary arms. So there was one auxiliary arm somewhere located over here, and there is another auxiliary arm over here. Now this early auxiliary arm which was there present in the classical model over there is something which is missing in this particular model. It just has one auxiliary arm and the main classification arm over there taken down. So this is the implementation which we are going to make use of today, and this is what's directly available on PyTorch for download. Now for the beginner part of it, it's pretty simple. Now since it takes a bit longer to run these ones, I have actually executed them ahead of time, and we are just going to do a plain walkthrough. So for you guys can actually clear, because the one which you get it on your GitHub repository, that's the one which is pipe cleaned of all the internal variables and anything. So anyways you will have to run the whole thing over there. Now it would take a bit longer. The earlier ones which were quite easily running down within seconds and maybe close to a minute, this one takes roughly about 8 minutes per epoch to get over. Now that's the only difference which comes from. So what we have is in the initial part is our first part of the header, which is just to look into whether everything is present over there or not. Now once our header part is over, next comes down the data loader over here. Now there is something you need to be a bit careful on the data loader. Now while we were using 224 x 224 sized images for our VGGNet, and that's what the ImageNet itself comes down with. But then for GoogLeNet, they had to make a bit of change. It was more of with the architecture, and so that the data does not get into the vanishing point over there. So for that, the data which this particular model takes down is 229 x 229. Looks a bit weird, but then you have to deal with it. It's always intrinsic property of the network which you are using. Now what you need to keep in mind is that we had earlier as well looked into this data scaling factor, and instead of using ImageNet dataset, we are using the CFAR10 dataset for our purpose over here. Now what we do is all of these CFAR10 datasets are something which comes down in smaller sizes of 32 x 32 sorry 64 x 64, and then we needed to always enhance it out. So today what we are doing for this one, quite unlike the VGGNet where you were scaling it up to 224, this is getting scaled up to 299 x 299. So this is the pixel span for each of these images. Now this part of the code is pretty simple. It just so this is my transform definition over there, and then in my trained data sets over there, what it does is it just looks into whether the data is available, otherwise it downloads it out, and then you apply this transformation such that this train set over here is something which is which has images of the size of 3 for the 3 channels cross 229 x 229 over there. Similarly, you do it for the test data set as well, and then your data loader is appropriately defined so that you can load it down from your train set or test set, whichever you need it. Now once you run this one, so if your data is not downloaded, so apparently we try to flush it out every time we do a new run just to see on functionality. So you see this one, but then you might if you are running down on a preloaded data set which you already have with you, you might not be getting down these lines over there as well. Now, the next part is to look into the total number of samples. So, yes, CFAR 10 was with 60,000 samples, and what we had done is we took down the first 50,000 samples for training and the 10,000 samples for validation. And then this is quite the way similar as we had done with AlexNet and then subsequently with VGGNet itself. So, there is nothing which changes over there. Now, for the reference architecture, the picture which I had shown you earlier for the model is what is hyperlinked already over here. So, you can as well click and go into that hyperlink and look into the network in a graphical form. Now, on the other side of it, this is an unrolled version of the complete network. Now, what typically they do is that it tries defining inception modules itself and then appends up the inception module with the main network, and that's how you do it. In between, you also have these extra auxiliary arms. I am just trying to inception blocks, and then it keeps on going. So, each of those A, B, C for each of these layers is what you had on the table which we had done in the earlier class, and you find the same thing written down over here. Now, that is quite a big network which goes down, and then this one is the final part of it, which is what we needed to look into it. Okay. So, the final part is where you have 2048 features which are linearized and coming out, and since it was done originally for the ImageNet challenge, so you had 1000 classes over there to classify, and that is why your output features from this fully connected layer is 1000, and then you had your bias over there. Now, the point over here is to look into what is the total number of parameters which you will be learning. So, what we end up doing is for each of these layers we try to put down for each of the inception blocks and everything coming down what is the total number of parameters, and then this is a total detailing for each of them, and once you finish it off you see that you are somewhere over here which is with 27 million parameters. So, it is 27,161,264 parameters which are there which you need to learn over here. So, now what we need to understand is that since this network was originally defined for 1000 class classification, but then we are changing it down to just a 10 class classification. So, there has to be a modification. Now, one of the modification is what you would do at the end of the fully connected layer over there. So, at the end when you had just 1000 classes to classify over there, so instead of 1000 classes you are now left with just 10 classes. What you need to also keep in mind is that somewhere in between you also had this auxiliary arm. Now, this auxiliary arm is also something which you will have to modify, because you cannot have 1000 classes coming out of the auxiliary arm, because it still gets down only for 10 classes. Now, that is where you need to modify the whole code for two different parts. So, one is that this part which is my auxiliary arms classification output. Now, let us get back into my actual network over here. So, on my network, so one is this end part over there. So, if I draw it somewhere close. Yeah, one is this last part which is my linear. Now, this in this linear one is where I will be making this 1000 to 10. So, that is the second part of my change which I am making. So, I just make this connected from 1024 onto 10, and then the other part which I need to change is somewhere up where I have my auxiliary classifications. So, let us keep on going, and I have my auxiliary inception auxiliary over here, my auxiliary classification, that is meant my aux logits. Now, over there I need to change this linear which takes in inputs of 768 features and connects it to just 1000 layers for classification. So, I need to convert this one from 786 which maps down to 1000 to 786 which maps it down to 10, and that is the change which comes over here. Now, what we are essentially doing is we are just replacing out the structures over there essentially with these structures. So, it is a pointer remapping which goes on, and the rest of the transfer function keeps on remaining the same. Now, this is what we have been doing for VGGNets, and over there it was just one arm which produces your output, then it makes it easier, but here then since it is two arms which produce the output, so you have to make down two changes over there. Now, after that we go back with our original form, and which is just to do copy down my weights and keep them for our later on visualization at later on point of time. Now, once they are done, then I check down whether my GPU is available, and then I define my criterion. So, Now here we are just going to train it down following the classification pipeline, and for that reason we are just using negative log likelihood as my criteria over there, and my optimizer over here is Adam, which I am just going to follow down. So these are plain vanilla dependent and taken down in the same way as we had done in the earlier ones. Now from there we need to start training down this network. So what we do is, you need to keep two things in mind. One is this no more has just one loss function, but it has two loss functions which you need to evaluate. So whenever you are taking it down, you need to have these independently evaluated, and independently either you can plot it down for your convenience, but then you need to evaluate each of them because the backward would require each of them to be done independently. Now from there we start down, and this is a training which we do just for 10 iterations, 10 epochs over there. Now the first part is where you zero down all of these buffers over there, and then you start your epoch counter. Now within your epoch counter, we just do my train data loader. Now my data is getting loaded into batches, and each of my batches is of 32. Now it depends on the kind of a machine on which you are running, whether you what you would decide as your optimal batch size. Now you can keep batches as small as even 4. This pretty much you can bring it down to even 1 based on what we had done in the earlier examples on batch learning versus sequential learning versus whole epoch learning. So it's just differences which crop up over there and how you are going to make use of that one. Now other than that, it's generally suggested that you keep down your batch in a convenient way which occupies a decent portion of your available RAM space over there. So if your GPU RAM on which you are running, or maybe your CPU RAM on which you are running, if you can take down batches of the size of 64, then please put 64. If you're limited by 32 or something, then put down smaller numbers like 32 or 16, any of them. So that's totally up to you. We over here have a convenient option of doing it down with a batch size of 32. Now over here what you do is, if I have my GPUs available, which for me is fortunately there, and I just need to typecast all of my variables over here. So once the typecasting is done for the variables, then I need to typecast my network over there, and then once everything is done, now you do a feed forward for the network, and then you find out what are your predictions, and then you find out how many of them are correct over there or not. Okay. Otherwise your data is not converted any further to CUDA, it's just typecasted into a variable, and then you have your forward and your prediction, and these computes coming out over there. Now the next part which comes out is you need to find out what is your loss, and now based on that you will be starting your backpropagation over there. Okay. Now once your backpropagation is done, we just have our optimizer coming into play, and this is Adam for us, so without much of an issue. And then what finally you have is something like you are just going to take down your losses and keep on accumulating, and so that you can plot and actually see what is the amount of changes which come down. Now once that is done per epoch, now within one epoch, once you finish down all the batches and everything, so that part is done. Now the next part which comes into play is that you are going to actually do a feed forward and then deploy and see down what's the kind of a performance you get down at the end of training it with just one epoch, and then with the next epoch. So that's the validation part of the code which we are running over here. Now once that's done, this is your plot function over there, and just to come out over there. So now since it takes a good amount of time, so typically it takes about 8 minutes per so this will so if you look over here, it's about 7 minutes 46 seconds, 47 seconds. So that's roughly close to 15 seconds short of a minute, sort of 8 minutes. That's what it starts down with. Now initially it starts with a training loss of something about 0.4, then goes down to 0.37, then 0.3, and then you keep this one. You see that this one keeps on decreasing. It starts with accuracy. Let's do it. So it starts with the testing accuracy of 52, then goes to 64, 68, 73, and it keeps on increasing. And then somewhere around 10 epoch, it's already at an accuracy of 80%. So if you look down at your main loss and auxiliary loss, you would see that they are steadily decreasing over there. Now one question does definitely come to your mind, that auxiliary arm is something which is not so deep over there, it's from a shallower region, and that's showing a lesser error as compared to your main arm over there. Now, in that would definitely mean that your auxiliary classifier is able to classify better than the main classifier. Now, you need to keep one thing in mind, that this is already a pre-trained model. This wasn't a model which was taken down from scratch. This is something which got imported from a model which was trained to solve the ImageNet problem, and they were all modified for your actual natural images and how to understand. So, the features are possibly something which are not changing. Now, the only change which was happening within your main arm and auxiliary arm was the new modification of weights which came down. Although we did not put a hard imposition that we are just going to modify only this layer at a time, but then since everything else is not going to get down much of an error, and that error on the rest of the layers is going to be 0. So, the only change which will happen is only at the random weights which are there in the auxiliary arm and the newly incorporated main arm for rest of the cases. Now, this is the kind of losses which you would be seeing down for your train and test, and this is the accuracy which you would be seeing down for your train and test, these two. Now, obviously, one thing you need to see is that your training accuracy still keeps on increasing, while the test accuracy is increasing, but then the rate at which it keeps on increasing, there is some sort of an influx, and then it keeps on slowing down over there. Now, my testing case accuracy is now already something which is very close to 80%, while my training is something which has already overshot 90% over there. So, that's just a initial level observation, because we haven't yet saturated it out. So, this has just been trained for 10 epochs, and if you keep on training for longer, you would definitely come down to a much more convergent point over there. The next part which we look into is we copy down the weights after training such that we can actually visualize it out. So, on my visualization part over there, this is what we look into the first convolution layer over there, and the first convolution layer was just a 3 cross 3 convolution layers, and then you had 1, 2, 3, 4, 5, 6, 7, 8 and 4, that is 32. So, you had 32 channels coming out from the first convolution layer, and then this is what they look like. Now, these were the initial weights which had been given over there. Now, after you had trained it out with this particular data set on CIFAR, this is the change. But then if you look into the differences which come down, they are not much of a differences. So, there have been a slight changes in the shades or one particular color channel over there which is just changing, not something which changes majorly. And one of the reasons why the changes are really low in terms of their intensity is because the earlier trained model was already taken down for natural images over there, and you are also dealing with the same kind of a natural image problem over here. Now, this is to look down into the convolution of one of the kernels for your second layer. Now, what you need to keep in mind is that since your first layer had 32 channels which are coming out, now we just had 32 which is each of these convolution layers, but this is only for one of these kernels. Now, if you look over there for the differences as well, you see not much of a change, and a majority of them are still flat, which is just 0 valued changes or near 0 valued changes which comes from over there. So, that is all what we had to do with GoogLeNet. Now, there is not much of things to say around with it these days, but then the main point which you need to keep in mind is that given that there are two different cost functions which you had to evaluate over here, that was one of the main reasons why you did take a lot more of time. But then given the other fact also that despite all of this being over there, you are able to come down to convergence much faster, because you see that you had started somewhere around roughly a rough guessing estimate of 50%, and then within 10 epochs you are already at 80%. So, that is a very rapid rise. Now, what definitely does come to play is that epochs are not always a consideration of it, because you also have more amount of time taken per epoch. So, if you take a consideration that the product of time taken per epoch into the total number of epochs, then that comes into an interesting play. So, somewhere later down when we are going into more of practical buildings, we will be seeing down like what is a more preferable network to take at a given place given all of these aspects, and also the inferencing aspect taken down over there. So, this was about going very deeper with convolutions with GoogLeNet, and then in the subsequent lecture I would be telling you about two more networks which are quite recent from 2016 and 2017 CVPRs, and they are based on something called as a residual network and residual connections, and networks with very dense residual connections, and subsequent to that we will be doing their labs as well. So, with that stay tuned and thanks.